Okay, so just like all of the units so far, now that we've learned another function, we're going to perform transformations on this function, right? So all of the same rules are going to apply. It's just going to look a little bit funny now, though. Here's what the equation technically looks like. This isn't on your formula sheet, right? Because it is still just the general rules, but we can make sense of this. A is still going to be your vertical stretch out front there. K is still going to be your vertical translation, right? Still the number hanging off the end. The only thing that's different here now is that your B and your H are actually up in the exponent. But that makes sense, doesn't it? Because these things are attached to the x value, and the x value is up in the exponent, right? That's pretty much it. Everything else kind of stay the same. So here's all the same rules you guys are probably used to seeing with mapping notation and everything else. So let's just do an example here. So for the following exponential function, describe the transformation as well as any effects on domain, range, asymptotes, x-intercepts, y-intercepts, and end behavior. Okay, so first thing I'm going to do, I'm going to rewrite this thing a little different. Let's rewrite this as y is equal to -10. Here, give myself room here. Y is equal to -10 to the power of 3x minus 9 plus 4. All right, so let's write this out. So we have a vertical reflection. Well, maybe just write it as so vertical reflection in the x-axis. Right? Just because of, well, why do we have a vertical reflection? Yeah, it's like a negative a value, right? So vertical reflection. We have a vertical translation. Vertical translation of 4 up. What else? We've got a vertical stretch, sorry, horizontal stretch of what? Yep.
1/3.
1/3, yep. Perfect, 1/3. And then a horizontal translation of what? Yep.
3 to the right.
Yeah, good job. I was trying to trick you there. So some of you guys might have been saying of maybe 9 right. That wouldn't be correct. Why wouldn't that be correct? We can't see the b currently the way it's written, right? So we're gonna write this a little different. This will be y is equal to -10 to the power of, and then I'm going to factor out a 3, even up in the exponent there. So that's going to be 3, start a bracket, and then x minus 3. So now we have a horizontal translation of 3 right. Okay, so that's all of our things. So now if we, well, let's see. So let's actually figure out now maybe our y-intercept and our x-intercept. So if we did our y-intercept here, so our y-intercept, then what should we do to figure that one out? If we're looking at this function, either one of them, it wouldn't really matter here. What are we going to do for our y-intercept? What's equal to 0 at our y-intercept? Yeah, the x value, right? So let's throw a 0 in, see what we get out for y. So we'll say, okay, y is equal to -10 to the power of 3 times 0 minus 9 plus 4. Okay, so y is equal to -10 to the power of -9 plus 4. And we end up getting 3.9 repeated. It's like very, very close to 4, but not quite 4.
Because it got like so small and then added 4. Well, that's what happened.
Yeah, if you think about it that way, right? It's like, because the -9 part, that's like 1/10 to the -9, right? So that's pretty much 0. It's like almost 0. Or so then plus 4.
It's pretty much 0, but it's not.
It's pretty much 0. It's so close to 0, but it's also infinitely far away from 0. So
Yeah, we could get closer. closer.
Okay. So then X-intercept.
Oh, just a second. So
X-intercept here, so we're going to, well, in this case now we're just going to throw in 0 for Y, right? So in this case it would be 4 minus 0. This is the original. Wouldn't really matter, but I'll do it this way. 4 minus 0 is equal to 10 to the power of 3x minus 9. So then we end up with just 4 is equal to 10 to the power of 3x minus 9. Okay, so we haven't actually learned this, have we? How do we get that x out of the exponent, right? Like, we don't have any algebra skills for this yet. Any ideas on what we could do up until the point we learned this? Yeah.
We can equate the constants.
Right. We can graph both of them, right? So I could graph this as my y1. I could graph this as my y2. And if you do that, you end up getting x is equal to 3.2. All right, next one. So it says, explain using transformations why the graph of y is equal to 1 over 5 to the x is just a reflection in the y-axis of the graph of y is equal to 5x. Do you think you guys are bright? All right, so I'll write it out here though. So let's say if we had 1 over 5 to the power of x, right, like this function here, then I just want to show that we could rewrite this thing as, well, 1 over 5 to the x, that's the same thing as just 5 to the power of negative 1 to the x, or like times x up in the exponent there, right? Do you guys see how that just is my a value? And if I have a negative a value, then that thing is going to, oh, sorry, that's my b value, I mean, sorry. A negative b value is going to reflect this thing across our y-axis there, right? So it just is the same in that case. So if we drew this out quickly, I'll just kind of show you what I mean by that, right? 5 to the power of x here, this one, would be a graph that looked like this, going up, getting bigger and bigger. And 1 over 5 to the power of x would look very similar, but it goes this way. Do you guys see how that is just like a mirror image over the y-axis? It is a reflection, so they are the same. Okay, let's get into some practical applications of this. Okay, so changes in populations, whether growth or decay, can be modeled by the formula y is equal to ab to the x, or y is equal to ab to the power of t over p. And that's kind of just a new little part I'll explain here in a minute. So a is going to represent your initial population. And just to kind of make sense of this, if you had your graph, right, and it was going up like this, if our population is like our y value going up and down, that makes sense, right? Our a value is our y-intercept, so that's going to be our initial population. Yeah? And then our b value represents the multiplier. So if it was like, what's the doubling time for this thing, or how long to triple it, or go up by, 70% or something like that, that's going to be where the b comes in, what we're actually multiplying it by. X is going to represent our unit of time. So same thing here, right? It's going to be our x values going across the bottom, or x like this. And then here, this is kind of our new thing here. So t represents a length of time, and p represents a period of time, such as doubling period, right? It's like, so this will really be like our x value here. And why this still makes sense, I think it does in the next question a bit more, but let's say that the question told us that it took like, 2 years for things to double, right? That's like our doubling period that we had. And then it told us that 6 years went by. Well, if it was written like this, then that would be like 6 over 2 years for our doubling period up top there. So that'd be 3, right? So this is just really telling us how many doubling periods happen. Or if the question was half-lives, if it says that the half-life of some radioactive element is like 2 years and 6 years goes by, then that would be 6 divided by 2. That would be 3 half-lives have happened. That's all that is when there's like T over P. Okay? We'll do some examples though. So this one says in 2001, the population of Sylvan Lake was 7,500 people. If the population increased at a rate of 4.5% per year, write an exponential equation to model the population growth. Okay, so we're really looking at this one, right? Y is equal to A, B to the X. So then filling that in, Y is equal to, and then what would our A value be? Yeah, 7,500, right? 75, that's our initial. That'd be like our Y-intercept. And then here's the big question. What's our B value going to be? If this thing is increasing at a rate of 4.5%. Yep.
0.45.
Okay, so let's throw it in 0.45. 0.045, are you thinking? Yeah, for 4.5%. Okay, so now just looking at that, now if we put X up in the top, right, for years, won't that thing be getting smaller? Right, I'm multiplying by a number between 0 and 1. That thing actually be getting smaller really quick, wouldn't it? I'm kind of finding 4.5% of 7,500 every year, right? This would be like a decrease at like a really fast rate, right? We want to increase at this rate. What's another way that we can increase at that rate? Yeah.
Wouldn't it be 1.045?
Nice. Perfect. Let's change this up a little bit. Well, first off, let's just do this. If I multiply by 1, right, no matter what X was here, that would get me to where I started, right? Multiplying by, 100% just gets me the number, right? Just to where I started to begin with. So I'm going to start at 1 and then add my percentage there. So 1.045. You guys see that? So if you're getting bigger, it's going to be 1 and then that number. Good? Okay. That's one not to get confused. So I'm going to put a star on that. Yeah. Okay. So then once we do that, then it says determine the population in 2016. So it says in 2001 this was the population. So we're going to have to go 2016 minus 2001. So 15, right? There's 15 years that have gone by. So then we're just throwing in the number. Y is equal to 7,500 times 1.045 to the power of 15 years. Okay.
If it was 4.5% for 2 or 3 years.
So that ends up being 14,514 people. And just always check to make sure your answer kind of makes a bit of sense. That answer kind of makes a bit of sense, right?
You get 0.
If you got like a really funny number out of this, chances are you did it wrong. Yeah. Okay, the population of mallard ducks in Canada can be represented by this function, where X is the number of years since 1975. Is the population increasing or decreasing? What do you guys think? Increasing or decreasing for mallards? Yeah, decreasing. How do you know it's decreasing? It's less than 1. What would you say it is? It's decreasing by how much every year? By 5%. Good. You see that? So if it's 90, like what we're doing here is we're finding 95% of it every time, right? So you would say that this thing is decreasing by 5%, right? So it's always like, yeah, like I explained it. Anyway, so decreasing because B value is less than 1. Okay, how many mallards were present in Canada in 1975? We shouldn't have to do too much math here. Sorry, I should be asking there. Yeah. Yeah, how do we know that it just is this number? That's our start, right? That's our A value. That would be like our Y-intercept. And 1975 is where we started, right? That's where they told us to start, like we started counting. Was that 1975? So that would just be 173. And then this is our A value, right? Okay, how many years passed before 1/2 of the population remain. Okay, so here's how we can do it. Let's start writing it. So I'll say like y is equal to, and I'll write my number out again, 173 times 0.95 to the x. Okay, so looking at this, what we're looking for is we want to know what x is, right? Because x is our years that have passed. When the population is half of this population, right? Because that's where we're starting. So what should I be putting in for my y value? Yeah, half of that, right? I can figure out what half of that is, and then that can go in there. So we'll say, okay, that number, just writing it over on the side for a second, like divided by 2 is equal to 865,500, right? So that's what we're going to replace with y here. So is equal to 173. Okay, so again, I don't have a good way to solve for x yet. Like we will be doing that, right? We'll be learning ways to solve for x when they're in the exponent. I don't have a great way yet though, other than graphing it. So at this point, I could graph this one as y1 and this one as y2, but it's gonna those numbers are big. You know, like it's gonna be kind of hard to find my window settings. It's gonna be kind of a pain in the butt, right? What could I do to simplify this down a little bit before I do that? All right, let's divide both sides by this, right? By our original number there, and divide by. Some of you guys might be thinking I'm working in circles. I kind of am, right? Because what is this? If I divide the top and bottom there,
1/2.
that'd be 1/2, right? And that makes sense. The one's half of the other one. So that would be equal to 0.95 to the power of x. So now this will be a lot nicer to graph, won't it? I could graph that as y1. I could graph that as y2. Now, does anyone see the shortcut that we could have taken right off the bat here? I did this by finding like half of the mallards and doing all that, right? What I could have done right from the beginning here is I could have set my equation up as y is equal to, well, why not 1 times 0.95 to the power of x, right? I know that you can't have like, you know, half of a duck or a mallard, but it should work out. I could actually throw whatever number I like into that one. I could throw 10 and call this one 5. I could make it 20 and call this one 10. It doesn't really matter what numbers you throw in, as long as this value here is half of my original value, right? I didn't need to actually have the actual number of mallards there because I just wanted to know the amount of time that goes by for whatever population to divide to go in half. Okay, so it didn't really matter there, so we didn't have to deal with those big numbers. But okay, either way, if you graph that, figure out where they intersect, you end up getting x is equal to 13.5 years. Okay, radioactive decay or half-life. Okay, so it's actually the same. It's going to be like the same type of principle here. So the same formulas can be used in this application as the population, yada yada. So half-life is a representation of the amount of time it takes for the radioactive particle to reduce to half of its original amount. Each time period sees the previous amount halved. So this means that the multiplier b must be a half. So that's kind of the idea. If you guys get a half-life question, then it's going to be y is equal to a, and then your b value will be a half. And then it would probably be t over p, because we have to know like how long that half-life period actually was, right? So that's going to be the idea. As soon as you see half-life, you should be throwing in a half for your b value. All right, so here's an example. It says Neptunium has a half-life of 396 days. A sample of Neptunium 235 has a mass of 250 grams. So write an exponential equation that models the amount y remaining after t days. Okay, so let's write just going to write the equation out again. Y is equal to A times B, and I'm going to write it as T over P in the exponent. Sorry, that's a little hard to read there. And then let's just fill in what we know. So Y is equal to, what should our A value be here? Yeah.
250.
Yeah, our initial sample, right? That's how much we started with, so 250. What should our B value be? Half, right? We're talking half-life here, so it's, they're saying for a half. And then our T, well, let's do the bottom number first. What should the P value be? Yeah.
396 days.
Yeah, 396 days. And then you could put an X or a T up top if you like. I'll keep it as a T. And there you go. That's our equation. So just remember what I'm looking at here, right? With this T over 396. It's not that complicated. It's just asking you how many half-lives have gone by, right? So if it takes this long for one half-life, if I had, you know, double that number up top and then just divided those, you'd end up with 2, right? So you're just figuring out the number of half-lives that are actually happening. Okay. So describe the transformation represented by the function in part A compared to the base function of f of x is equal to 2 to the power of x. Right? So what are the actual transformations that are happening here? Okay, well, if we, here I'm going to write one more time. So we've got y is equal to 250. And then I'm going to write this a little bit different though. Instead of 1/2, I'm going to write this as 2 to the power of -1. Right? Be the same thing. And then times T divided by 396. And now it's a little bit more clear what's going on here, right? So we have a vertical stretch of what? 250, right? That's like our A value, right? So it's like our A value is 250, so vertical stretch of 250. We've got a horizontal reflection in the y-axis, right? And that's because of our negative B value there. We've got a horizontal stretch of what? Yeah.
396.
396, right? Because this T over 396, right? That's like 1 over 396. So it's the same thing. It's going to be the opposite of what it actually is. So that would be a horizontal stretch of 396. Okay. Now, what mass of Neptunium-235 remains after 1,000 days, rounded to the nearest tenth? Okay, so now we're just kind of plugging it in. So we'd say y is equal to 250 times 1/2 to the power of, I never leave myself enough room, 1,000 divided by 396. Okay, and you could just plug it all in. Make sure you're careful that you're only raising the half to this, right? Don't go 250 times 1/2 to the power of that, right? It's only the half that's being raised to that power. And just know this too, that 1,000 divided by 396, that's really just like 2.52. And I think that's repeated. So that's really just saying there's been 2.52 half-lives that have occurred, right? That's all that you really just found there, right? So if you plug all that in, you end up getting 43.4 grams.
How many moles, Tyson?
Yeah, that'd be the next part, yeah. Okay, so when will the sample be 50 grams? Okay, so we're looking for the time now. So in this case, it's going to be, well, 50, that's our y value, right? So we're going to say 50 is equal to 250 times a half to the power of t over 396. So then, yeah, we're kind of at the point we can graph this. You may want to divide both sides by 250, right? That might be a bit easier if I go divided by 250, divided by 250. So that ends up being what? 50 over 250. So that's equal to 1/2, and then t over 396. And then if you just graph both sides, right? Just graph this as y1, this is y2. We end up getting t is equal to 919 days. All right, last one. This one's pretty interesting, though. Yeah, get it? No. All right, so the formula for compound interest is a variation of the exponential growth decay formula. So here is our compound interest formula. It's not on your formula sheet. It would usually be given to you in a question, but I've seen it where it hasn't. So it's a good idea to memorize this one. But if we break it down, it's not as confusing as we think. And even what we're looking at here, let's go through that. Compound interest. This is actually a really common way that banks figure out interest. Let's say if you guys take out like a Visa or something, or a loan. These things are done through something called compound interest. And in short, what it's doing is it's figuring out like interest of the interest, right? Over like whatever compounding period you decide. So let's go through this and I'll kind of explain a bit more. So it says, so A will be the amount of the investment at any time t, right? So A is like how much money you are getting out of it, or if you had a loan to the bank, how much you owe the bank, right? So it can go either way, right? If you're investing in the stock market or investing in something, then this formula would be good for you. If you're borrowing money, then this is money that you'd be paying to the bank, right? So it can be good or bad. So that's how much it'd be coming out. Your P, often called your principal, is the amount you start with, right? So that would be like your investment or the amount that you borrowed from the bank, right? So that makes sense, right? This is like your Y-intercept on the original. That was like your A value from before, right? Like Y is equal to A, B to the X. This P value is like our A value, okay? Now this part looks confusing, 1 plus R over N, but what's happening here, the R is our investment rate written as a decimal. So if you just ignore the N for a second, or say that N was equal to 1, then this would be like A is equal to P times, and then 1 plus, let's say that your interest rate was like 5%, then that would just be 0.05, right? Which that would all just be 1.05. So the same thing we were doing before, right? That's just like what it's going up by or what it's going down by, right? So that didn't really change. The new thing here is this N value, right? There's two of them. We're dividing by N there, and we have it up in the exponent there. N stands for the number of compounds per year, like how many times it happens per year. Another way of thinking about that is it's like how many times you look at it per year. Okay, so if something compounds semi-annually, like we're going to see in a second, what that means is that you get a certain interest rate, but halfway through the year, it's going to look at that interest rate, and then you're going to be paying interest on that interest. Does that make sense? It's like just looking at it twice throughout that year. Because here, let's even back up a little bit more. I think it's worth going through. The simple interest formula is I is equal to PRT. So this would just be the interest is equal to your principal. So let's say this was like $1,000 times your rate. So let's say this was like 0.05, so 5% or something. And then for 1 year, so let's say like 1. Okay, so then this would be like $50, right? So what we're doing here, what they're doing here with the compound interest formula is this situation was just over the year. That was like for 1 year, right? They only looked at it at the end of the year to figure out how much money you owed. But with the compounding interest one, they actually look at it twice throughout the year. And another way of thinking about this too is that if I threw into this equation like 2 for my compounding period, then my rate, if that was like 5%, well, now it's only going to be 2% because you're dividing it by 2. But then you're raising it to a power, and that power is going to grow faster than the divide, like going to the power of 2 is going to raise faster than dividing by 2. If that kind of makes sense. Yeah. Okay, yeah, for the most part though, it is kind of a little bit of a confusing formula, but that's the idea. It's like how many times you're looking at it through the year. If you guys want more after, I can kind of show you how these would end up working out to the same thing in the end if you just looked at it 2 times or 3 times throughout the year, if you just got interest on your interest. Okay, so different terms here though. We've got annually, your end value would be 1, right? You're only looking at it once a year. Your semi-annually would be twice, quarterly would be 4 times a year, monthly would be, there's 12 months in the year, so 12 times a year, 52, or compounded daily is 365. This is one thing that actually kind of took me by surprise. I didn't really realize this with the Visa that I had, and actually most Visas nowadays. They do compound your credit cards daily. So if you have a big purchase, like you say you buy something for like $5,000 or something, then you're actually paying interest on that every day. It's not like the full, let's say if your Visa is like 20% interest, you're not paying 20% on it every day, but you would be paying 20% divided by 365, right? So you pay that small amount of interest on that every day that goes by, right? So that's something to be aware of now. It didn't used to be like that. It used to be as long as you paid everything off by the end of the month, then you'd be good and you wouldn't pay interest on it. But now you do. Whenever there's actually money sitting on that Visa, you're paying for that. Not a ton, right? Because it's a small percentage, but it could add up if you like go all month, not paying that thing off, and then you pay it all off right before the end of the month. I always thought that meant that you were good, right? You did what you had to, but you would have to pay interest for those 29 days, right? So I hate that. Like I think it's a little bit shifty, but just be aware of that. Let's look at this example. So it says the student borrows $2,500 to further her post-secondary career. The bank is charging 6.5% interest, compounded semi-annually. So write an exponential formula to represent the situation. So semi-annually, that means our end value is going to be 2. So then just throwing it into the equation up top there, that'd be A is equal to 2,500 times 1 plus, and then our interest rate would be 0.065, right? Just that written as a decimal, divided by 2. And then that be to the power of 2 times t. Okay, and we could simplify that. Let's write that as, here. A is equal to 2,500 times 1.0325 to the power of 2 times t. Right, just kind of simplifying all that middle stuff. Okay, so now they're saying if it takes the student 5 years before she can repay the loan, so if we just throw 5 in for t there, we end up getting A is equal to 2,500 times 1.0325 to the power of 2 times, and then I'm going to throw 5 in for the time, right? So we get $3,442.24. So how much interest will she pay on the loan if she takes it out for 5 years there? So what should we do here?
Wait, we solve for amount of money or the percent?
The actual like interest, the amount of money, yeah. How much? Yeah, money. Yeah.
When you just subtract 2,500 from the value.
Right. So in the end, right, she ended up actually like she borrowed this much, and it ended up getting up to this much. So you're just going to subtract those two, right? And that would be the actual interest that she would pay on the loan in the end. So 2.24 minus 2. So she ended up paying $942.24. Which, yeah, isn't nothing, right? So just be aware whenever you guys take out loans or anything else, that is real money. Sometimes it doesn't feel like real money, but